Hi, welcome back. So this is lecture 21 in this course on Bayesian modeling. So in the previous lecture, we have seen prior predictions and posterior predictions and how to generate these prior predictions and posterior predictions in R. Okay. Just to recap, prior predictions are the model predictions that you generate before seeing any data. So it's in the planning phase of the experiment. So let's say you are already planning the experiment, but you haven't collected any data, but you know what kind of outcome you would expect in this experiment, right? So even before seeing any results, seeing any data, you would specify your likelihood assumption, that what is the underlying generative process behind your data. That's your likelihood assumption, and your prior assumptions about the parameters, right? So given these two sets of assumptions, this you can call your model. So this is your model, the set of likelihood assumption and your prior assumptions. So given these prior assumptions and the likelihood assumption, you can predict data for your current experiment. Okay, so these data are called prior predictive data, right? Similarly, after seeing the data, you can again generate predictions from the model for some future experiments. How do we do that? Because after seeing the experiment, you can compute the posterior distribution of parameters. Okay. Now, this posterior distribution is your knowledge about parameter values after seeing the data and given your prior assumptions as well. Okay. So, given these posterior distributions, now you can generate posterior predictions of the model, right? And then you can compare whether those posterior predictions meet some future data or not. Okay. Now, why we are talking about prior prediction and posterior predictions? Because these two kind of predictions make a very useful step in model building in the Bayesian framework. Why? Because prior predictions can be used to assess whether our priors that we have chosen are reasonable or not, whether we have made reasonable assumptions about the priors or not. So, for example, if your priors are completely unreasonable, then what happens is that you end up generating prior predictions which are completely off, which do not really look like the kind of outcome you would see in the experiment, right? So, your prior distributions, your prior assumptions are reasonable if your prior predictions look similar to what kind of similar the kind of outcome you would observe in the experiment. Okay, so for example, you cannot have prior distributions that would generate prior predictions which are in the range of, let's say, 20,000 milliseconds of reaction time, because you cannot have that long reaction time. Okay, so that's the utility of prior predictions in assessing whether your priors are reasonable or not. Okay, of course, you cannot use prior predictions to specify your priors. It is just a check whether you are doing something completely wrong in specifying the prior distributions, right? The use of posterior predictions is in assessing whether the likelihood assumption that you have made, is it a reasonable likelihood assumption or not. Okay, of course, it is not a test of how good is your model in terms of predicting future data. It is just a test of whether your likelihood assumption is reasonable or not. For example, you can be in the situation where you're trying to model reaction time data. Okay, so let's say you are doing some decision making experiment where you have some decision times data and you want to model the decision times data, right? Now, suppose you assume that these decision times come from a normal distribution. Okay, that's your likelihood assumption. Now, this likelihood assumption is not really reasonable, because normal distribution generates negative reaction time as well as it is symmetric, and that's not how the decision times typically look like. So, it's not a very reasonable assumption. Okay, so this can be checked using a posterior predictive check. So, posterior predictive checks will tell you that a likelihood assumption of normal distribution is not very reasonable given this kind of data, and maybe a log normal distribution would be much more reasonable. Okay, that's the goal of this lecture, that we are going to see how to do posterior predictive checks, that how do we do posterior predictive checks and how they are useful in checking the validity of our likelihood assumption, whether we have made a reasonably good likelihood assumption or not, right? But again, just a word of caution, this is not a hard test of deciding what kind of likelihood assumption you should have, or not a test of model's performance. It is just to ensure that the likelihood assumption you have chosen are reasonable or not, right? So maybe in a set of 4 or 5 possible likelihood assumption, it would tell you which one you should throw away, which one is a completely bad likelihood assumption. That's what it can tell you. Okay, so let us see how. So we will do posterior predictive checks in R, but before that, let me describe you the process, how the posterior predictive checks look like. So you know, so at this point you know how to generate posterior predictive data from a model. How do we generate posterior predictive data? So let's say X obs is the observed data that you observed in an experiment. And you assume, this is your likelihood assumption, you assume that xi, that data in ith trial comes from the underlying function f of x theta. Okay, so this is your likelihood assumption. And then you make some prior assumption about the parameter theta. Let's say theta comes from p of theta. Okay, this is your model so far. Then how do we generate posterior predictive data? We will first estimate posterior distribution of theta given this data x obs, right, which is basically likelihood of theta given x obs prior distribution of theta divided by marginal likelihood. So once we have posterior distribution of theta, okay, now we can generate posterior predictive data like this. So you can call this as the step 1. So what is step 1? Estimate the posterior distribution. Estimate the posterior distribution of theta. So that's step 1. What is step 2? Draw samples from posterior distribution of theta, basically p of theta given x obs, and then conditional on each sample from the posterior, we are going to generate data, so x spread from our likelihood assumption, where theta is basically a sample from the posterior distribution. So how do we do this? You can actually do it like this. So let's say you run iterations from I to, let's say, 1 to n, from I in 1 to n. So n number of iteration. In each iteration, you will draw a proposal theta I from posterior distribution of theta given the data. Okay, and then conditional on each theta I, you will generate predictions. So this will be a posterior predictive sample. How? So generate predictions from f of x given theta I. Okay. So this is the process. So this will give you posterior predictive samples. You have done this earlier in the previous lecture. Once you have these posterior predictive samples, then our goal, step 3, would be to compare x spread. Okay, so this is the posterior predictive data against x obs. So actual data that you observed in the experiment that you have used to train your model. Okay, so we compare x spread against x obs. Okay. So that's your next step. All right. So let us see how to do this in R. Okay. So let us take the same example again, where participants see a sentence on a screen, okay, and their goal is to judge whether the sentence on the screen is acceptable or not. So they will respond with a yes or no. So for example, they see on a screen, key to the cabinets are rusty. Okay. Now the sentence is not acceptable for most speakers, so they would respond with a no. Okay. Our goal is to record the judgment times. How much time do they take to judge the sentence? Okay, so we are recording judgment times and we want to model judgment times. Okay, so let's say judgment times are called denoted by RT, right? So our likelihood assumption is this, that reaction time or judgment time in the ith trial comes from a log normal distribution with parameter mu and sigma. So this is our likelihood assumption, and our prior assumptions about mu and sigma are these, that mu comes from normal 6 0.5 and sigma is equals to fixed as 0.25, right? So these are our prior assumptions about the parameters. Okay. Now suppose RT obs is the actual observed data in this particular experiment. Okay, and let us visualize how the actual observed data look like. So this is how the actual observed data looks like, right? So this is the actual data, right? Now how do we do a posterior predictive check? So first step is to estimate the posterior distribution. Okay, how do we estimate the posterior distribution? So one simple method that you have seen is this, that take a lot of values of mu, parameter mu, in a certain range. So here we are taking 10,000 values of mu between 4 and 8. These are equidistant values of mu between 4 and 8. Now for each value of mu, we are calculating the likelihood. What we are calculating here is joint likelihood, because you do not have a single observation, we actually have 50 observations. Okay, so what we do is that we calculate likelihood for each observation corresponding to each value of mu, and then we multiply likelihood across all these observations. Okay, so in this case, let's say you have 50 observations, so you will calculate a likelihood for each observation, and then when you multiply likelihood of each observation, right, then you get a joint likelihood, which is basically likelihood of joint occurrence of these 50 data points, right? So that's what we are calculating here. So we calculate joint likelihood for each parameter value, and then we calculate prior density for each parameter value. Then we can calculate unnormalized posterior, where we multiply just likelihood and prior, and you can visualize how the unnormalized posterior looks like. So this is how the unnormalized posterior distribution looks like, right? So at this point we have estimated the posterior distribution, right? Now step 2 would be to draw samples from the posterior distribution, because this is a posterior predictive check, right, not a prior predictive check. So we draw samples from the posterior distribution of mu, and for that what you can do, you can use a sample function. So we are drawing samples from mu x, weighted by its unnormalized posterior density. Each sample is weighted by its unnormalized posterior density, and we keep replace true, right? So this will end up giving us a posterior distribution, right? So end up giving 1,000 samples from the posterior distribution of mu, and this is how their histogram looks like. All right, now I will go into generating posterior predictive data. So this is step 3, generate posterior predictive data. Okay, so I'm taking how many samples? 1,000 samples. So I want 1,000 posterior predictive samples. You can decide 500, 1,000, 2,000, right? So I would advise that you have at least 1,000 samples, so that to properly visualize, because there is randomness, so you won't see enough in 50 samples. So try with 1,000 samples. Number of observations is 50 here, right? So I create an empty data frame for posterior predictions, right? Now I iterate through each sample, and for each sample I collect a sample from the posterior. So this mu sample is a sample from the posterior. Then I simulate future data conditional on this sample mu, which is from the posterior distribution, and I simulate n obs, that is 50 observations, and then I store it in the, so this will give me basically a single posterior predictive sample, and then I store it in the overall data frame for the posterior predictive samples. Right? So when I run this loop, this will end up giving me a data frame containing 1000 posterior predictive samples. Okay. Now I can create another data frame that will store the observed data, because I want to compare observed data against posterior predictive data. So it would be useful to have this data frame. Okay. So df obj, it has other columns the same. The main thing is that this RT pred or whatever the reaction time in this particular data frame would be RT obj, right? Now let us visualize how posterior predictive data looks like and how observed data look like. So our goal is to compare them. Okay. So let me call it a step 4, compare posterior predictive data against observed data. Okay. So that's what we are going to do here. So this function is going to generate the posterior predictive samples, right? So I'm using zzplot function. This is going to generate the posterior predictive sample. So I do not want to generate too many. Let's say sample ID is less than 500 or so. Okay. Okay. So this plot shows you posterior predictive data. So that means given this data and given these likelihood and prior assumptions, this is what you would expect in future experiment, right? So whatever observed data you would have in future experiment would be somewhere along this distribution, right? So the value is somewhere between 100 and let's say 500 milliseconds. Right? Now let us compare this with actual observed data. So in this plot, I'm basically plotting all these posterior predictive data as a gray color, and I will plot the observed data as red color so that we are able to see it properly. Right? This will be in red color. You can also set up line width. So let's say line width is 1.5 or something. Okay. So actually this is showing you, I want this color to be gray. We will see why it is not gray, but this is showing you what we expected. See, so all these light red lines are the lines which are indicating each posterior predictive sample. Okay, so each of these light red lines are indicating posterior predictive sample, and this dark red line is indicating the observed data. And what you would see if your likelihood assumption is correct, if your likelihood assumption is reasonable, what you would see is that this observed data would be somewhere in middle of this band, of this light band created by posterior predictive data. See, so the posterior predictive data creates a band of this distribution, right? So there's so it allows all these distributions, right? The posterior predictive data, and the observed data should be in between all this, right? So that means this is a reasonable likelihood assumption, right? If this wouldn't have been a reasonable likelihood assumption, you won't see this. So another things that you can do, so see this is gray now, so this is much better. So you can see these gray lines are indicating the posterior predictive data and the red line is indicating the observed data. Okay. If you want, you can make this plot black and white so that you can see them clearly. This plot shows you that your likelihood assumption is a reasonably good likelihood assumption given these data, because the observed data is in between these bands created by posterior predictive data. So this is called posterior predictive check. So we're just visually inspecting this. There is a way to do this posterior predictive check numerically as well, which we will see later on. It's not a main point here in this lecture. Okay. We're just seeing how to do this posterior predictive check visually. Okay. Now let us take an example. Basically, for the same data, what if your likelihood assumption is different? Okay. So let me just let us do exactly same things, but with a minor change in our likelihood assumption. So let us say, rather than assuming that these judgment times are log normally distributed, what if I assume that the judgment times are normally distributed with mean, mu and sigma, where mu has a prior of, let's say, 350, okay, and sigma is fixed at, let's say, 50, okay, and RT obs remains the same, so we are not going to change RT obs, right? And let us do everything now. Now our likelihood assumption has changed. Prior assumption has just changed accordingly, because now mu parameter is in the scale of 300, 400 milliseconds, right? It's not on log scale, it's on raw scale, right? So let us see what will happen now. So to calculate posterior distribution of mu, now you can generate, let's say, reaction times between 100. You can generate values of mu between, let's say, 100 and 500. Length equals to 10,000. Okay. And corresponding to each mu, let us calculate its likelihood. And prior is 350. Okay, something wrong here. So this usually happens when there are too many data points. For simplicity, let us just reduce the data points for now so that we can do these computations. So let's say you have just 20 data points rather than 50. Okay. So now it would be better. What happened? Okay. Maybe you can take 10. D norm, RT obs. Oh, sorry. So there's a mistake I did here. So that's why. Okay, okay. Let us see this again. Okay, fine, fine. So it can work with even 50 data points. I just made a mistake here. Okay, so this is our posterior distribution of mu now. Okay, what had changed? Our likelihood assumption. We are assuming now that the likelihood is a normal distribution, right? Now let us draw samples from our posterior distribution, which was step 2. So this is how the posterior distribution looks like. That the value of mu is somewhere between 230 and 270 milliseconds, whatever, right? Now let us generate posterior predictive data. So you're following exactly the same process. Only thing that will change is our likelihood function here. So rather than generating from log normal, we generate now from normal distribution, and this will be 50 here. So let us see. Okay, so we have generated posterior predictive data, and this is our observed data. And now let us compare posterior predictive data against observed data. This plot will show the posterior predictive data. Okay, so this is the posterior predictive data, different samples of posterior predictive data. Now let us compare it with observed data. Okay, this is what you see. Now this observed data looks slightly off from the posterior predictive data, because posterior predictive data says that your distribution of reaction times would be symmetric around the mean and always going to be positive, but the observed data tells you that it is slightly skewed on the right hand side. You will in fact see that the observed data would even violate the basically the posterior predictive check, especially when you have more data points. Okay, so for fewer data points, it's not very clear what is exactly happening, but you can still see that the observed data in its shape, in the shape of this distribution, looks very different from the posterior predictive data, which is predicted by the model, right? So there is one more thing that you can do, which is that you can compare summary statistics of posterior predictive sample and summary statistic of observed data, right? How? So let's say this was your posterior predictive data. Now you group it by sample ID, and you summarize certain summary statistics. So mean RT predicted by the model is mean RT pred. STRT predicted by the model is STRT pred. Let's say we also do max and min. Max RT predicted by the model is max RT pred. Min RT predicted by the model is min RT pred. Okay, so I've generated these summaries corresponding to each sample ID. Now you can plot them. Okay, easy plot, aesthetic. Let's say mean RT. Let's focus on mean RT first. So draw a density plot of mean RTs. Now you can add a vertical line which shows the actual observed mean RT. So mean RT of observed data. So mean of RT obs. Okay. So need this library. Okay, this is how it looks like. If you want, you can also draw histograms instead. Yes. Okay. So the histogram shows the distribution of mean reaction time predicted by the model. Okay, and the red line here shows you the mean reaction time in the observed data. Okay. Okay. So here we are comparing summary statistics of posterior predictive data against summary statistic of observed data, right? So this is a very useful tool, especially when it is difficult to compare the actual distribution of observed data and posterior predictive data, right? So you can compare summary statistics. And importantly, why this becomes important is this, that if you compare some more important summary statistics like max RT in this case, or let's say upper quartile or something like that. So this is just to illustrate. So let's say you compare max RT. Let us see how max RTs look like in observed data and posterior predictive data. See, now this is very fascinating. So the max RT in all posterior predictive samples are in the range of 320 to approximately 440. Okay, so that's the range of maximum RT in posterior predictive samples. But the observed data shows the max RT of 480 or something. So it's completely different. This summary statistic is completely different from posterior predictive data. Can you speculate why? Because the likelihood function we assumed here was a normal distribution, right? So we were generating those posterior predictions from a normal distribution. And as a result, a normal distribution wouldn't generate those extreme maximum observations, right? So maximum RT, the posterior predictive samples are going to have are up to 440 or so. Okay, because you assume there is a normal likelihood. So when you're generating from normal likelihood, it is going to generate symmetric observations. It is not going to generate extreme observations, basically those long tails in the right hand side. But the actual data does have those long tails in the right hand side direction, right? So actual data can go up to 470, 480 milliseconds, right? So that's very interesting. Let's see what happens with minimum RT. I think minimum RT could be fine. I don't see there could be big discrepancy in minimum RT. Well, even in minimum RT, the actual observed data has minimum RT of 100, but the posterior predictive check says that it is somewhere between 80 and 200. So it is in fact pulling it towards the mean because it has to be symmetric, right? You can also compare SD, let's say SDRT, and here SD of RT obs. That's also very different, right? So the observed data has a very large standard deviation, but the posterior predictive samples have a standard deviation between 40 and 60. So on these summary statistics, the posterior predictive checks tell you that your likelihood assumption is not reasonable, that you have probably assumed a wrong likelihood function. Okay. Otherwise, most of these summary statistics would be within this gray band. Basically, they would align. So the observed data, the summary statistics of the observed data and summary statistics of posterior predictive data, they would look similar. They would basically, at least you would see this red line within this gray region, right? Let us see whether they look aligned when you assume a log normal likelihood, right? Let us do the same things for our previous assumption when you assumed a log normal likelihood. Okay, this was the case of log normal likelihood. Okay, this was for log normal likelihood. So let us see what happens. Let us try to draw same plots. Okay. So yeah, here. So this is for mean RT. So let us first do for mean RT. Mean RT looks exactly in the middle, so it's very good. So when our likelihood assumption was log normal. Let us see SDRT. SDRT also looks somewhere in the middle, right? So it aligns really well. Let us see what happens with min RT and take min RT obs. Okay, so this has same problem. So the mean RT in observed data is very small, but the posterior predictive checks that this can be larger, longer, right? So it does not do really well in this particular aspect. But let us see max, and there is a reason why it doesn't do well, because in reality the observed data in these decision time experiments do have shifted reaction times, and that was not taken well when we generated this data. We can come back to that point later. Max RT. So let us check how the distribution of max RT looks like. This is doing fine. Okay. So what we have seen is that the posterior predictive checks can tell you whether your likelihood assumption is reasonable or not. So when the actual data was log normally distributed, we checked whether how the PPC, posterior predictive checks, look like when you assume a log normal likelihood versus when you assume a normal likelihood. So when you assume a log normal likelihood, which is basically more reasonable assumption, you see that the red line, the observed data, is actually in middle of these posterior predictive checks. So posterior predictive distribution looks almost same as the observed distribution, right? And that also checks for all the summary statistics of posterior predictive data and observed data. But if the assumption is that you assume a normal distribution, then the posterior predictive checks looks very different from the observed data, right? So these were for the cases for summary statistics. See, for summary statistics, the observed summary statistics look different from summary statistics of posterior predictive data when the likelihood assumption is normal. Okay. So this is it on posterior predictive check. So in this lecture, we have learned how to generate posterior predictive data in R and how to compare this posterior predictive data against the observed data. So the data we already have that we have used to train the model. If the posterior predictive data and the observed data look same in certain summary statistics and in their distribution, if they look similar, that means your likelihood assumption is reasonable. If they look completely different, if they look very different, then your likelihood assumption is probably unreasonable. That means you need to change your likelihood assumption. That means you need a better likelihood assumption. Okay. So it's a very useful tool during modeling. So always during modeling, we will develop this practice of generating prior predictions from the model and generating posterior predictions from the model and doing those prior predictive checks and posterior predictive checks to verify whether our assumptions are unreasonable or not. Okay. So this is it in this lecture. Next lecture, we will see the workflow of model building in the Bayesian framework. All right. Thank you very much.